Hello and welcome to today's webinar, Risk-Free Reservoir Monitoring Tracer Technology. Thank you for taking your time out and being here with us today. This is our third webinar in English out of series to come, and this time we're going to focus to the Inflow technology. My name is Asel and I am the marketing manager here at Resman, and with me today I have Bashar, our regional sales manager in Middle East based in Dubai, and Eliana, our reservoir engineer specialist based in Stavanger, Norway. As usually, before we start, let me explain how you can talk to us during the webinar today. We are planning to have 15 minutes Q&A session in the end of the webinar. So if you have the questions along the way, along the presentation from both Bashar and Eliana, just put them in the questions area on the right side of your screen, and we will make sure to answer those questions and as many of them as possible. And those of you who are joining a little bit late, don't worry, we will be sending you a recording of the session when it will be available. So with that, I think we are ready to start really, and I would like to welcome Bashar to proceed with our presentation. Bashar, please.
Thank you very much, Asel. Hi, everyone. It's very good to have you around. So I will today explain to you the technology that we have, the Inflow technology. That is one of the multiple technologies that Resman do provide. So we've got the first one, the Inflow technology, and we've got the pumpable tracers. The pumpable tracers has been explained before in one of the previous webinars, and it's mainly about injecting tracers, when the inflow tracers are the ones which we would install permanently into the well, and that will help us to understand about well cleanup, about the productivity of the zones and the qualitative inflow from each of the monitored zones. So if we think about it, so excuse me just a second, I'm trying to get myself around the yep. Okay, so the way we always think about it is that we as petroleum engineers or reservoir engineers or production engineers, we're sitting in the office and we always wonder, how is my reservoir performing? And multiple questions do come in our minds, and that questions would be, one of them would be, how are the layers in my reservoir producing? We would like to know how is the layer producing in my reservoir, and it's a very important question, obviously, to understand, because you want to know how is your layer productivity and how much are you depleting from each of the reservoir layers. Am I having production from all my layers, or all my monitored or all my producing zones? Am I experiencing any type of crossflow? Has there been any changes to the productivity that I have within my wellbore? I'm seeing a decrease in the water, the level, the flow rate in my surface, but I don't know where is that production coming from. So this is a question that I'd like to understand, which layer is causing that. I'm seeing a water breakthrough, but where is that water breakthrough coming from? So the tracer systems would help you identify that. The question that comes up into my mind, and which we always think about, is that I want to perform a PLT run, for example, or I want to do a surveillance, but then I don't know when to go and take that action. And to know when to take that action is, obviously, you want to know that, am I seeing any changes happening on my wellbore that gives me let me say, the good justification for me to go and perform a surveillance in the well. So all of these questions that comes in my mind is like questions that you'll always be sitting and thinking, how can I get these questions answered? And then this is exactly the reason why I consider Resman for Inflow technology as being a dream come true. And the reason for that is that because what it provides, Resman Inflow technology provides a cost-efficient solution that maximizes the value of the information for the clients. And the way it does that is that by first of all, it provides a risk-free and interventionless technology. And by that being said in its own self, is that means you would run it in your hole, you would keep it down there for as long as up to 10 years, because it provides up to 10 years of continuous monitoring. So you put it down there in your well, and you run it along with your completion string, and you keep it down there for up to 10 years. And during those 10 years, you can at any point of time collect samples at surface and understand what's happening in your well without having to shut in your well, without having to intervene, without having to rig up and rig down equipment. I mean, it's just take samples at the surface. Um, so it provides you with the zonal inflow quantification. It tells you how much is flowing from each of them, from each of the zones that you have a tracer system in front. And at the same time, it gives you information about, am I seeing any pattern changes in my flow? Am I seeing oil flow from all the zones? Am I seeing water flow from all the zones? Am I seeing gas flow from all the zones? Am I seeing one of them drop out and not produce, for example, oil? So that gives you that you can get to see that all by just taking samples at surface without any intervention into the wellbore. And moreover, as I mentioned, it gives you information about the water and the gas water breakthrough, the water and the gas breakthrough. So, which is a very, very important information that we all as reservoir production engineers are looking to know. Where is my water coming from? And when it starts, I want to know if it's coming from the toe of the well, coming from the mid, coming from which layer. So all of these questions comes into your mind, and the technology will help us to solve these questions. So now, just to get some definitions out of the way, and I'd like to explain that out, is that the tracer system is a polymer that is embedded with a tracer, and the tracer itself is an organic, non-toxic chemical that we take and we embed into the tracer, into the polymers, into the polymer rods, and then this together is called a tracer system. Now, this tracer system is then integrated into a carrier, and the carrier is what would fit into your completion string, and it's what would carry the tracer systems down into the wellbore. Now, it's very important to note is that we have up to 60 unique oil systems, and we have up to 60 unique water systems, and we have up to 13 unique gas traces available. And with that being said, that means we can provide monitoring of up to 60 zones for oil and water at one point of time. So yeah, I'll go ahead here to explain something a little bit about the tracer themselves. So as I mentioned, these tracers are synthesized by Resman, and that what makes them special, and that what makes them is that we synthesize them based on the requirement, based on the need of the wells and the design of a well-to-well basis. They're not radioactive, and there's organic chemicals, as I mentioned. So the properties that we have to know about the tracer systems is that, first of all, they are, as I mentioned, designed to spec, designed to the well parameters that we have: temperature, flow rate, if we're going to be using chemicals in the well to stimulate or to while producing or while shutting in the well. So we get all that information during cleanup, what's the fluids in the well bore. So we get all that information, and then these all information are used to design and customize the tracer systems for the client. Now, the tracers are designed to be dormant, and when I say dormant, that means the oil tracer will remain dormant until it encounters oil, and the water tracer will remain dormant until it encounters the water phase of the fluids. So by that mere fact, that means when you are producing a well and you have a low water cut, that means your water traces are not being releasing, and as soon as the water system starts producing, then you will see a tracer signal that comes out from the water traces. The other thing is that the tracer systems are designed to have a constant release rate. So what does the constant release rate benefit us? The constant release rate benefits that we can guarantee that over the course of period that we say we are going to give you, your client comes and say, I want 10 years, then we know that over the 10 years period, we know how much would the tracer be releasing over the 10 years of its service and its installation in the wellbore. And then this obviously its own self characteristic. That means we know that this is how much the traces are going to be released every day, and then we will use that as well to help us with the interpretation of the signals as we go on, as we perform interpretations. So just to give you an information about that, so the pressure range that we're dealing with is like we have dealt with pressures up to 21,200 psi. The temperature range that we have worked with is from 10 to 200 degrees C. And as I mentioned, the longevity for the oil systems is up to 10 years. The longevity of the water systems is up to 7 years. The system does not, I mean, H2S and CO2, once we know about it, we can design it and it will not affect our tracer systems. And then, yes, obviously, then the dimensions of these tracer rods are made to fit into the housing of the tracing carrier. So they're all fit to design and fit to how we want it to go and where to go. Yeah. So this just gives you an information as well about how we can integrate this into different options, completion options. So for example, the first one on your left-hand side, this is it's an ICD, and you can integrate it into an ICD if you want to, and then that it will just the trace systems would be integrated down there. Or you can integrate it into an outward vented carrier or a sand screen, and then that will be maybe before an ICD or just a normal sand screen. We can even do it on a cemented liner application where you would just run it along with the liner, and then you can cement around it, and then you can perforate through them. So the application, as long as we have a method to transport the tracers from surface and along with the wellbore and keep it in the monitoring zone of interest, the tracer systems, they can work. It's just a matter of how to get it down there. Whether it was a cemented liner, we can do it. Whether it was with an ICD, sand screen, tubing, with a liner, whatever the method is, it can be done. Now, just to go on with the methods of analysis that we have. So now, once you have done, we've got two different types of analysis. We've got a transient analysis, and we've got what we call a steady state analysis. So the transient analysis gives us information about the cleanup efficiency of each of my monitored zones. It gives me information about how much is each zone producing. And now, why is it called transient? Because we induce a transient effect in your wellbore by shutting in the well for 6 to 12 hours. 12 hours would be the optimum time. Shutting the well for 12 hours, induce that sort of a transient effect when you're having a tracer cloud building up in front of the zones. And then when you open the well, it flows back to surface with a transient sort of with a different signal that I will show you in the next slide. But then on the steady state part, we do not shut in the well. We do not induce any type of transient effect. We just collect the samples as the well is producing. And then what we're looking at the constant release of the tracers. That was one of the properties that we're looking at, which is a constant release of the tracers, and we just accounting or looking for that constant release of tracers. So now for the steady state, obviously this can be done on a weekly basis, can be done bi-weekly, can be done every month. I mean, and then it just depends on how often we want to collect samples and how often we want to be monitoring our wells. So now let's simulate the transient analysis that I was mentioning before. So what happens is when you shut in your well, you get this tracer cloud buildup. And then when the tracer cloud builds up and then you open your well, the tracer cloud that has been built up in the zones starts flowing up the surface. As you know, what happens at the beginning, you start seeing a high concentration. And then as time passes, you start seeing that concentration decaying and becoming less. Now, it will become less and it will reduce until it gets to the constant release of the tracer systems. And then once it gets to that, you would get a plateau line, which is, as you can see at the end where it says steady state, it would be just a plateau line that just goes through, and that would be the constant release, as I mentioned before. Now, if we observe the two different curves that we have, You have the orange curve, which let me say had the higher peak, and it went very fast to the steady state level. When the transients, when the blue line, it took a longer time for it to get to the steady state levels. Now, what does that tells us? That tells us a simple thing just by qualitatively looking at it is that the orange system that we had in the first zone was a stronger zone that just kicked out all and pushed out all that tracer cloud and tracer slug into the wellbore and into surface. When the blue system, it had some difficulty in pushing that system and pushing that tracer cloud out, which tells you that this zone is a weaker zone compared to the orange zone, for example. So this is just qualitatively. And obviously now when we come to the quantification part, this is something that Eliana will be discussing on the next slides. But then this is just qualitatively, and that just gives you an information by looking at the transient analysis. Now, obviously, steady state analysis, if the zone is not producing, then you would see no tracer coming from that zone. So that would give you, just by looking at the steady release of the traces, you can know if the zone is producing oil, producing water, or producing gas, and so on. Now, just to put the whole concept in perspective now, so what happens is the process would be we would get the tracer systems, we would run them into the wellbore. The tracer systems will start releasing into the flow. You will start collecting samples at surface, and then these samples, once collected, we take them to the lab, we analyze them, and then we perform an inflow interpretation where we look at the transient analysis, whether it was transient, whether it was steady state analysis. Then once that is done, we would integrate that data into Petrel. We have a Petrel plugin available, and it's called Resvis. So we can integrate that data into the Petrel, into the Resvis plugin, and then easily you can see what was your production rates or what was your contribution at any point of time. And it captures the history for you. So now just to have that again and just looking at the bigger picture together right now. So what happens is if you have one well, and let's say this one well, you've got 3 systems installed with tracer systems, you're able to identify what's flowing from each zone, what's the percentage, if you're seeing all zones producing or not. Now let's look at the field development on a field-wide perspective. If you have, as I mentioned before, we have 60 unique oil and 60 unique water. If you have those 60 unique oil and 60 unique water spread it around on the different wells that you have in your field, then what you can do from one sampling point, you are able to identify which zones are flowing from which well and which zones are not flowing from which well just by collecting a sample at one sampling point. So if we think about this, this is a dream come true, where you are able to identify what is happening in your reservoir by collecting one sample. And obviously you would from one sample, let me say today, one sample in a week, one sample in another week, without intervention, without any sort of without any intervention, without breaking up, breaking down, or doing anything of that sort, you just know everything about your field. So this is a dream come true, and yeah, I just hope that you share me the same passion that I have for this technology. Thank you very much for attending, and I'll back to you, Asil.
Yeah, thank you, Bashar, for the presentation, for the introduction part. And I see already there are some questions coming in, so keep them coming. We're going to answer them in the end of the session. And now we have time to investigate some case studies. And therefore, I would like to invite Eliana to continue with the presentation. So, Eliana, please, the floor is yours.
Thank you, Asal. Thank you, Bashar, for the presentation. So my name is Eliana, and I'm a reservoir engineering specialist at Resman. And in today's presentation, I would like to present you 4 different cases to explain how the inflow technology works. So yeah, it's running. Before going to the actual field studies, I would like to take this slide for explaining how the Resman tracers will actually benefit the monitoring of the entire well life cycle, and furthermore to benefit the reservoir management of the field. So we have different modes for monitoring of the well. One of them is a cleanup. So often the operator is interested in knowing whether all the zones are cleaned up or not, whether they are flowing or not. So we can also advise them for implementing extra cleanup operations where the zones are not flowing and improve the well productivity of the well. Oh, I didn't want to zoom in. So if you can help me, Asel, to
Yeah, sure.
that.
See. Just
I think it's not working. Yes.
Yeah.
Thank you. Now we have a multi-rate test, which is another monitoring mode what we usually use for determining qualitatively which zones are contributing oil or water at different flow regimes or different choke settings. Through this test, we are also able to see the dynamic response of the reservoir and determine high or low pressure zones, determine possible formation damage zones, and so on. Then we have a restart. And in this restart, we can actually quantitatively assess the productivity of the well. That restart is often carried out after a temporary shutting of the well, when we will create the transient conditions for applying a flu shot model, which is an in-house model that is developed by Resman and help us to quantify how much is produced in each individual zone. And lastly, during a secondary recovery, which is a very common stage in which the well will go through, we can use a steady state or continuous monitoring for assessing where the water is coming from and where is the water breakthrough in which point in time appeared. So that can be water breakthrough or gas breakthrough, depending on the stage or the implementation in the field. And lastly, we have we can also benefit the tertiary recovery when we can actually optimize the polymer fluiding or any other tertiary recovery technique that is implemented in the field. And we can also confirm EOR or IOR before the full field implementation. So let's go first, before going to the actual study cases, through the fundamentals of the flu shot model. And that is to explain how is actually made the quantification. So we have, in this case, 2 monitoring locations, and we want to create some transient conditions which are created right after a well shut-in. So in this case, we see many inflow points coming from the reservoir into the wellbore. And for this example, I have stated the inflow rate in Q2 or the zone 2 to be double the inflow rate in zone 1. So what happens here during the shut-in is that the tracer concentration is built up as a cloud. This is the polymer tracer that is actually located between the screen and the base pipe, and the tracer concentration is distributed uniformly in the annular space. So after some time, when the well is opened up to flow, the cloud is flushed out up to the surface when some samples are collected to take to the lab and measure the concentrations. So I want to highlight that the higher the inflow in the zone, the faster the flush out of the cloud. So that is actually how the concentrations will look like at the surface. So we will see the cloud as a peak, and that peak will drop off until reaching steady state levels. That steady state levels corresponds actually to the direct release of the tracer. And what the model does is to compare the drop of the curve. So this is the expression that it describes the model. This is the K, that it's the rate of decline of each individual curve. And what we want to do is first to normalize the K for each zone and then compare them. So the higher the rate, the faster the flush out, and the higher the decay of the curve. So that is actually to show how the model works. And I'm gonna proceed with our first example, which is quite interesting because it provides us with a PLT comparison, as it's often that the operator wants to know what are the difference between these two technologies. So this is it's moving more backwards. Let's see. Yeah. So this is an oil well that it's located in the Gulf of Mexico. This is completed as a stack rack pack. So in this case, the tracers are loaded into sunscreens, and the zones are completed with gravel pack and annular isolation. This well in particular has varying sand quality and has higher shell content, especially in this zone in the upper part of the well. So for this case, they wanted to install four different tracers in each of the zones to compare the results with a previous PLT survey that was implemented in the well. So this is the response of the PLT. And what it says is, like for the lower zone, they got a contribution of more than 50%. For zone 3 and 2, it has an average of 20% of the inflow contribution. And in the last zone, which is the zone number 1, and had the very poor permeability, they got only 7% out of 10%, of course. Then this is how the tracer response looked like. And let's see what we got out of this. We got a very similar response in terms of the inflow when we compare PLT and tracer. So in this case, Resman provided a cost-effective and a low-risk solution to obtain important reservoir information. And the results are quite comparable to the results of the PLT. So the difference is the high risk that the Resman technology can offer without well intervention, and it actually will enable better well placement and completion design for future wells. Now we have a monitoring in a multilateral well. So this well in particular is in oil field located in the Norwegian continental shelf. This is a chalk formation. So this well is completed with lighting sleeves in the main bore and screens in the lateral. In total, it has 19 zones, and the operator wanted to monitor 5 out of these 19 zones with 9 unique tracers. So in this case, the tracer technology was actually chosen for monitoring the well due to the complex well completion and the complex trajectory. So this is a first cleanup campaign that they wanted to assess in the well. What it says is we have the mass tracer recovered versus volume in this case. And what it says is that the tracer located in location number 6 through 9, those located in the lateral, got a very good result. So they were actually flowing. So we see that the rate was increasing right from the very beginning of the campaign, and especially for zone number 8 and 9. Something different happened for this location number 7, located at the 2, which stabilized at this point in time. And we flagged here the lateral as a flowing zone with a high cleaning up efficiency, whereas the other tracer didn't show a response. So something happened there when we see that the tracer concentration is slightly increased at this point in time, and that event actually triggered zone number 1 and number 3 to start producing. So they started a slow cleanup, and we flag it here as a medium cleanup efficiency. Then we got the second cleanup campaign for this well, and this is a very recent campaign carried out at the beginning of this year, I guess. And this is a different story because we got a response from tracers located in the main bore and not in the lateral. That's what we see here in the color map. So zones number 1, 3, and 4, which are the ones that we got the signal, are actually flowing. So that actually enabled us to advise the operator on extra cleanup operations for that target zones, and in that way they could improve the well productivity. So this is a very interesting examples. If you may find additional questions, so please ask in the panel. We want to interact with you in the at the end of the presentation in the live session for the questions. So please go ahead. And now this is a water breakthrough case, which is an interesting case that we had in Russia. This is a horizontal well, 1 kilometer long. This is a highly fractured reservoir in a carbonate field, by the way. And the operator wanted to monitor the entire well by locating 7 water tracers and 7 oil tracers. So let's see what the tracer says. To the right, we see the water tracer response. So it is quite clear that this tracer is different to the rest of the zones. And that is, this is the water cut that is increasing actually from 2% up to 15%. And we see a very good correlation between zone 5 and the water cut at this point in time. So that we can also see that in the color map, which is the colors for the zone 5. It's highlighted in comparison with the other zones. So another thing that we can see here is this green tracer, which is actually quite low. And it means that it is not contributing to water production in this well, and that is that is located actually here. So with the oil tracers, what we can see there is that at the time of the water breakthrough, we see that the oil production slightly drop at this point in time. So this is a very good example and clear example on how we are able to locate the water breakthrough and locate exactly where the water was coming from. So in this case, or based on this water breakthrough findings, the Reservoir team adjusted the reservoir models and improved the management of the field water flooding program. So this included adjustments to injector well rates and a placement of future wells. In this case, Resman tracers provided an excellent fit to this application because the tracer systems were adaptable to the existing sunscreens, and it offered, of course, very low risk and cost-effective technology. And this is the very last case study that I have prepared for today's presentation. And this is a well that was completed with ICDs and swell packers. This is a sandstone reservoir, and the operator wanted to check the contribution along the production zone. And as this is a multi-rate, they wanted to evaluate the zonal contribution and the response at different rate changes. So they wanted to know where the reservoir pressure was insufficient to sustain the flow, and also to identify the water source, if any, in the well. Okay, so for this case study, for the water tracers and oil tracers both, we implemented 3 rate changes, and we see clearly where the response is applied. So that is the heel of the well, the yellow zone, and we see that the well is actually contributing to water at all rates. What happens with the red tracer, which is located at the toe of the well? It just increased very rapidly at a maximum rate. So that is in terms of water monitoring, and we can see that results flagged in this quick zonal production map. So that tells us for zone number 5, low drawdown and high drawdown is producing water, and for zone number 1, it's producing water only at a high drawdown. Then we have the oil tracer response, and in general, we can see that all tracers are contributing to flow to the oil production at all rates, but except for this blue zone and red zone, which suddenly drop off when the well was operating at a minimum rate. So yeah, that is in general the response of the multi-rate test. And with these results, we have checked the individual zonal behavior after changing the bottom hole pressures. We see that the zone 5 is a water shoot-off target zone, as most water comes from there. And also, we have targeted the water flooding, and we can advise, or we could advise the operator for reevaluating the water flooding strategy for this well. So the oil production could potentially be sustained by a water injector to target zone 1 and 2 for increasing the oil production, and this water injector should not preferentially target the zone 5, as most of the water occurs in this zone. Okay, so now we have come to the end of the presentation, and I am going to quickly summarize what we have covered today. We have seen general information from tracers. We have explained how Resman tracers can benefit the entire well life cycle. We have gone through different case studies in which I explained a PLT comparison and what the main difference was there. I have gone through a cleanup assessment where we were able to actually advise the operator on extra cleanup operation to target zones, and they were able to improve the well productivity. We went also through a water breakthrough case, which was quite clear and quite interesting to see. And we went through a multi-rate test in which we assessed the well productivity at 3 different operational settings. And we advised the operator on applying an increased drawdown to low performing zones. So I think for the production optimization loop, so typically the information derived from tracers is used for in the geoscience workflow in conjunction with other data to generate a more accurate understanding of the reservoir. So the operator can actually improve their static models and get refined simulation results from the dynamic models. So it can turn into a refined and better predictive reservoir models due to reduced uncertainty. It can help improve the forecasting, help predict better economics, and then they can go and history match and update the history matching to retrofit again the production optimization loop. So to conclude, how we can help our clients is by providing them a continuous monitoring solution, which is a piece of the puzzle that it can summarize in 3 different points. One is to reduce uncertainty. Second, to predict better economics for the development of the field. And third, to make better reservoir management decisions. So that is the end. I will go back to you, Asal.
Thank you, Eliana. Thank you for the good summary, and we hope that you liked the selection of the case studies that was presented today. If you would like to know more about any of the case studies, then just let us know, and you can reach us offline, and we can continue dialogue. Now it's time for the questions, and let me open up the questions, and we can look into as many of them as possible. So thank you to all who brought these questions in. So first question is, what are your plans and expected time scale for gas tracers rated at or above 150 degrees? So I think, Bashar, Eliana, we don't have detailed information right now to elaborate on this. We have a certain R&D process going on, and for the temperature above 150 degrees overall, we take it case by case, because it's not only the temperature range we are looking at, but certain aspects of the field. So the person who asked this question, if you have a specific interest for the gas traces above, for the temperature range above 150, we suggest you reach out to us over the email, and we're happy to continue dialogue with you on this specific matter offline. There are some warm greetings here, so really nice to see, and some good feedbacks among the questions. Let's look into this question. What does the lifetime of the tracer system depends on? So who would like to take this question?
Yes, I can take it.
Yeah.
So mainly the lifetime of the tracers depends on the amount of the tracer that the roads are elaborated with, and also the maximum flow rate of the well. But we do also consider some other designing parameters for the tracers that can be, as I said, the flow rate, which is quite important. The temperature, it's an important parameter for that. the water cut of the well, the expected water cut. We can also consider the oil density, and it is quite important to check the completion and the simulation fluids that has been used in that particular well. So every case is individual and should be analyzed case by case because it cannot be generic.
All right, thank you, Eliana. Can you retrofit existing wells with tracers? Somebody asks.
So I'll take that. I'll take that answer to that question. So can we retrofit? It just depends as well on a case-to-case basis. So the concept is if we are doing it on a liner, for example, that has been cemented, obviously we cannot retrofit. But then we had scenarios which we had before where we had where the client wanted to run a tubing into the perforated liner and install packers with sliding sleeve doors into the different sections of the producing of the production zones. So this is considered a retrofit of a kind because obviously it's a well that has already been done before. So it all depends on a well-to-well basis. But a retrofit, as in a piece that has already been installed and there is no plans to pull it back again, not an option. But then there's other options as well, which we can consider on a case-to-case basis.
Right, thank you, Bashar. Next question. How long does your inflow traces last for? I think Bashar, you mentioned that in your presentation, but maybe the person joined a little bit later. So could you just remind?
Sure. So for the oil systems, we've got up to 10 years of continuous monitoring. And for the water systems, we can go all the way up to 7 years continuous monitoring. So yeah, so simple answer will be 10 and 7.
Yeah, and here I also want to add, if you follow our news, it has been shared a while ago. We received a Resman globally, a research grant from Norwegian Research Institute to invest further into longevity. So we as a company continuously invest into increasing the longevity of our tracer technology because we believe it's really, really important. Next question, why are so many rods required for some applications? Who would like to take this question?
Diana, you want to take this? Or shall I take it?
Yeah, you can go ahead.
Okay, so great, thanks. So why are so many rods are required? So the concept of the number of rods is directly proportional to the amount of tracer systems we need. So that means if we want to monitor for a longer duration, and then it depends as well on the number of years that you want to monitor for. So if you consider that you want to monitor for 5 years or 7 years, let's say, then that would give you an X amount of tracer, an X, let me say, mass of tracers, and then that X mass will need to be distributed over the number of rods. So that means if you want to monitor for a longer duration, then you will need to have more tracer rods to carry on the tracer that will be sort of ran into the wellbore. Did I answer your question?
Let's hope so, Bashar. And for the person who brought that question in, please bring the clarification questions if something was unclear from the Bashar's answer. Another question is, it's actually 2 questions from the same person, probably related to the same thing. So I would just read them both and then we decide if we're going to take that one. So the person says, really surprised OS5 didn't show up unless the low pressure zone was not as permeable as the other sections. So Eliana, I guess this was a comment/question to one of the graphs in the case studies that you presented.
Yes, I would like to know which case study was that. Can it be a multi-rate test or?
OS5. So if we OS5. So yeah, the person who asked this question, could you specify which case study that was, if you remember? Because for us it's probably, if we scroll here, I think OS5 was from this one. Yeah, OS5.
And, can you repeat the question again?
Yes, yeah, the person says yes. So it's the person says, really surprised OS5 didn't show up unless the low pressure zone was not permeable as the other sections. Was it that, or was that the case or not?
Well, I don't think it's the case, because at this time we don't know the pressure that it's in this area of the wellbore. So if the person can clarify which case was that, we can actually address the question in a better way.
I think the person confirmed that was this field case number 2. Yeah, I think so. Cleanup 1 and 2.
Okay.
Yeah, the person says cleanup 1 and 2.
So yeah, it's that is actually the response that our tracers are given in this case, and neither of both cleanup number 1 and number 2, we got the response from that location. So it is yeah, it is most likely that this zone has a very low pressure there, and as those cleanup campaigns demonstrate that any flow was coming from there, we can see that we can actually this zone is in a low pressure zone.
Right. I think that's thank you for this question. There is more questions are coming from other people too, but for this specific case, I suggest we come back to you offline with more details, because as Eliana said, this was also a little bit quick walkthrough of the 4 field cases, and we understood you are curious to challenge a little bit on this case number 2, and we're happy to do that. Thank you for agreeing on that. We just try to, in the remaining 7 minutes, answer a few more questions from those which are coming. So let's see. What is the application of the different plots, i.e. tracer mass, tracer concentration, since different plots were used in the field examples? So it's again about some field examples. Eliana, do you want us to go back to one of the slides? If so, just tell me, where should I go?
It's okay. It's okay here.
Okay.
So as the person mentioned, 3 different plots, or 3 different ways of showing the actual concentration. We can find the tracer concentration that is directly measured from the laboratory. We can find the tracer flux, which is simply the concentration times the sampling point volume rate. And we can have also another measure that is the cumulative tracer mass, and that is actually the one that we see in this case study. And all of these measures depends actually on the campaign that we want to analyze. So for this particular case, it's a good idea if we have a cumulative tracer mass, which measures the buildup of the cloud and directly release of the tracer mass that is produced to the sampling point. So because this is accumulated, we can clearly see these kind of behaviors. And for other campaigns like the restarts, the transient campaigns, the cleanups and multi-rate, it is advised or recommended to use the tracing concentration or the tracer flux, which is a more direct measure of the concentration.
All right. Thank you, Eliana. One more question. What does the lifetime of the tracer system depend on? So who would like to take this question?
Yes, I can answer that question.
Yeah.
The lifetime, I guess we have explained it before. that the lifetime depends on the amount of the tracer and the maximum flow rate of the well. And we can consider other parameters in the well. So as I said, the temperature of the well, the water cut, the completion of and the stimulation fluids that was existing in the well. So this is a very specific case, a specific question that it has to be analyzed differently for every well.
Yeah, and if the person who asked this question would like to engage further into the dialogue and have maybe some specific references, feel free to reach us out, and we are happy to have the dialogue offline. And one more question, can you tell a little bit more about the type of carriers that are normally used for installation of traces?
Would you like to answer, Sharon?
Yeah, I can take that. So the way I'd like to think of carriers is anything that can carry that tracer down to the wellbore and along with the completion string. So that means we have done that on a stand screens. We have done that on a just a normal shroud where you have a base pipe from the inside and a shroud from the outside. We've done that on ICDs. We've done that on AICDs and with AICVs. We've done that on the on cemented liner applications. As I mentioned, when you run it with a liner and you perforate through it. So the way you think about it is that as long as we can just find a carrier will be just something that we can just attach to your completion string, and you can run it down to the well bore, and then the traces can be conveyed down there as well. So it's so literally any completion string, there will definitely be a method that we can latch our trace systems into it, and it can be used as a carrier.
Thank you, Bashar. I think that was a good answer to the question. I think we can take one more question before we need to conclude. So the question is it possible to carry out hydrochloric acid treatment of a well if Resman traces are installed in it?
You want to take that, Eliana, or you want me to take it as well?
Go ahead, Bashar.
Okay, so so the question about hydrochloric acid, so hydrochloric acid, as you mentioned, is used for, as you know, it's used for a stimulation. So the concept is the traces systems are designed to they're designed to specifications and parameters of the well. So if we know that the well is going to be stimulated with hydrochloric acid, or if we know that the well is going to be the well is going to be shut in for extended durations, or if we know, for example, that there will be H2S or CO2 in the well. So all of these are parameters that we take into consideration when we are designing the tracer systems for the well. So the answer to your question would be yes. The tracer systems will withstand HCl and hydrochloric acid with no problems. It's only a matter of us knowing in advance so that when we're designing it fit for the purpose that we want it to be, considering all these parameters.
Very good, Bashar. And I think this was the last question we could take in. Unfortunately, the time is really running, and we have a few more questions that we see, but we're gonna answer them offline. This is the third webinar, as I said in the beginning, out of series to come, and we are coming soon back to you all with the new content and new topics to be addressed. If you have any specific question that you would like our technology experts like Bashar, Eliana, and many more to address in one of our next sessions, just feel free to write us an email to communications@resman.no, and we definitely prepare something for you. Thank you for participating in today's webinar. We were really glad to see you all. Thank you for all your questions, and we hope to see you again next time. Goodbye.